Before I start my session on these small videos for you, I would like to introduce myself. I am Vishwajeet Poddar. I'm a chemistry faculty in Alt Academy and faculty for NEET chemistry. We have been regularly trying to come up with such informative lessons for you, which are not only relevant, but in our sense of understanding is very much appropriate for you too. And before I proceed further, I would like to let you know about myself a little bit. I have been into this industry for last 20 years and have been associated with a lot of organizations here in Delhi, which have got a great name. I am a graduate and postgraduate from Delhi University and have been an NTSC scholar. And as far as chemistry is concerned, I can handle, or rather handling, all the aspects of physical, inorganic and organic chemistry with equal ease, and have helped thousands of students to clear their NEET and JEE examination. And I think with my assistance, you will be in a position to score very high in your NEET examination. There are some small things that we would like to share with you. And as a part of our these sharing, I am starting with the first part of a topic which is often not understood very clearly. And I have tried to give these lessons in a very interactive fashion, which I hope you will be enjoying. The name of this small video is called as Resonance. And about resonance, we will be speaking a lot of things in our subsequent slides, and I hope you will find it enjoying as well as relevant for you. Okay, I have introduced myself. You have known me, but there are some customary things that I would like to know about the quality of broadcast. How do you find the quality of broadcast on the scale of 1 to 10? I would also like to know about your preparation state. This is myself, Vishwajeet Poddar, and then let us begin with our session on resonance. Okay, look here, trying to make it more interesting. We have a teacher and we have students also. So while making the topic understood to you, the normal query that is coming to your mind, I have tried to visualize that, and I'm trying to put that in a question format so that you can get the answer in our relevant subject matter. Look, when we speak about resonance, the first thing that comes to our mind is the structure of benzene. You might have seen, or you might have noticed also. Have you noticed that all the CC bond length in benzene are identical? Benzene does not behave like normal alkene, and none of the structures of benzene satisfy its true behavior. I would like to let you know about benzene, a couple of things. If we draw the structure of benzene like this and ask you, what is the CC bond length in benzene? We know that CC single bond has a bond length of 1.54 angstrom. CC double bond has a bond length of 1.34 angstrom. And CC triple bond has a bond length of 1.20 angstrom. We notice that the bond length in benzene is 1.39 angstrom, somewhere in between a single and a double bond. What has happened in benzene? What is so special that is happening with benzene that its bond length is somewhere in between 1.34 and 1.54? Neither it is a single bond nor it is a double bond. Moreover, benzene, like an alkene, like a normal alkene, if we are taking this as a normal alkene, or we take this alkene, it is not behaving like a normal alkene. It doesn't give all those reactions of those normal alkene. Like a normal alkene undergoes electrophilic addition. whereas benzene does not undergo electrophilic addition. It gives rather electrophilic substitution, but it does not give electrophilic addition. Okay, we'll try to explore further. Benzene has delocalized electrons, which means the pair of electrons are shared between more than two atoms. Now, we have the concept of localized as well as delocalized electrons. There are some, rather many compounds where we have localized electrons. That means electrons are static. And we have the theory for static electrons only. But when there are cases when there are delocalized electrons, and it is possible in variety of situations, as in the case of benzene, we have delocalized electrons. That means electrons are not concentrated at one place. When electrons are not concentrated at one place, that means the pair of electrons are shared between more than two atoms. And only high energy electrons can get delocalized. And such electrons have less force of attraction. All the kinds of electrons cannot be like this. They need to be high energy electrons for getting delocalized. You can very well ask, are pi electrons high energy electrons? Fine. Very true. Pi electrons never lie between two nucleus. As you know about the pi electrons, they never lie between two nucleus. They are in pure p orbitals. And therefore, they are subjected to less force of attraction. And pi electrons are mobile in nature and highly reactive. Now, again, the question can happen, can we call delocalization of pi electron as resonance? Well said. Yes, we can say delocalization of pi electron as a resonance, but think of it. If I ask whether electron moves in benzene or not, if we are saying it is delocalized, that definitely has a direct outcome that it is moving. But if electrons are moving, then the movement of electron is basically generating current. That means if you will be touching benzene, then it should give you electric shock, which definitely does not happen. You do not get electric shock. So if we are saying it is delocalized, it has got a different concept. Not exactly that electrons are moving. You should remember, if electrons are moving in benzene, then you will experience electric shock if you touch benzene, because movement of electron is basically current. Now, if all those things, electrons has to be delocalized and then it has not to move, then what does it mean? Look at this structure. This is called as orbital approach of resonance. Orbital approach. Look here. We have tried to draw the structure of benzene. Benzene is a planar compound. Look, we have made a plane and the p orbitals are above and below the plane. Now, p orbitals, they contain one electron. Look at this. These electrons can share, these two can share, these two can share. Or other way, these two can share, these two can share, or these two can share. It is their choice. We do not have a control over it. If such kind of sharing will happen, we can get a structure like this. If this kind of sharing will take place, we'll get a structure like this. But both these structures do not satisfy the actual structure of benzene. Actual structure is this. Actually, all of them overlap. There is annular pi electron cloud exists as shown. There is annular pi electron cloud that exists as shown. You can see this is annular pi electron cloud. Come to the resonance aspect of it. All the 6 pi electrons are overlapped. All the 6 pi electrons are overlapped. The two canonical forms or resonating structures are hypothetical structures, and none of the two is the real structure. These are the structures of benzene and none of them is the true structure. But you should know they are called as resonating structure, shortly called as RS. This is called as RH, which is called as the resonance hybrid. And the true structure is the hybrid structure. This is the only true structure. Resonating structures are hypothetical structure. But why do we draw? We draw it because as such we do not have a theory of mobile electrons. We have a theory of static electrons only. That's why we draw resonating structure to find it out. Okay. For every compound which shows resonance, we draw all the possible canonical structure. And due to delocalization, partial pi bonds are formed. Partial pi bonds are formed. This is what you are getting. You are getting bond length as 1.39. They are partial pi bonds. They are neither complete pi bond, nor complete single bond, nor complete double bond, nor complete single bond. They are partial pi bonds. For resonance, the presence of parallel p orbitals with high energy electrons coplanar to each other must be present. This is called as conjugation. You might have heard about conjugation. You might have read about that, like this compound has got a conjugation CH2, CH, CH, double bond CH2. This compound is called as conjugated compound. Why it is called a conjugated compound? Because if you draw these compounds, and here you will have p orbitals, pure p orbitals, and these pure p orbitals will be having one electrons which can combine with each other. Sometimes these two can combine, sometimes these two can combine. So this kind of conjugation happens. For resonance, the presence of parallel p orbitals with high energy electrons coplanar to each other must be present. This is called as conjugation. And for resonance, molecule should be planar. If resonance has to occur, the molecule has to be planar. Okay. Coming to some more aspects of resonance. Delocalized electrons have force of attraction of 3 nucleus, leading to more force of attraction, leading to decrease of potential energy. Suppose an electron is here. It is being attracted by this as well as this by this. So there are 3 force of attraction. And these force of attraction lead to decrease of potential energy, and therefore stability increases. And therefore we say resonance increases the stability. Why does resonance increases the stability? Because the electrons are pulled towards many other nucleus, which results in decrease in potential energy. Resonance hybrid is always more stable than any of the canonical form, because resonance is present in hybrid structure only and not in any canonical form. As we have shown you the resonating structure of benzene, we have resonating structures as well as resonance hybrid. In resonance hybrid, what we are saying generally, that the canonical forms, they are not all that stable, but resonance hybrid is more stable. And bear in mind that all the canonical forms should be nearly of same energy or stability. Okay. You had a question? Can you tell more about it? It is getting interesting. What do you mean by this energy? Well, I am telling you about this energy. There are other interesting information too. If a compound is having only one canonical form, then there will be no resonance. At least 2 structures are required for resonance to occur. Let us solve a small question. Let us have this question. HCH, C double bond OH, and there is a positive charge. This compound will have no resonance. This compound will be having no resonance. Why? As it has no second structure. It cannot be formed as a second structure. You may ask why it is like this. Suppose there are electrons here. Fine. Suppose you say this electron moves here. If this electron is moving at this place, what is happening? Just try to have an idea. We are having H, C double bond, C, O, H, and this is H here. And this positive charge has been neutralized. And now look at this oxygen. There are 6 electrons. This is a 6 electron, highly unstable. So we cannot form it, right? So this compound cannot have a second structure, And that is why we're saying if this compound is having 6 electrons, then this will be highly unstable and its energy will be very high, right? If among accepted canonical forms, stability order is C2 greater than C1 greater than C3, then the most stable resonating structure is a better representative of the true molecule. Most stable canonical form will have the most weighted average. So this is what is important. All the canonical forms should contain the same number of total sum of the shared electron pair and unshared electron pair. Again, we can have an example. Let us see. We have a compound RC double bond O and there is a positive charge here. You can as well understand here we have 2, 2, 4 and octet that is completed. Now look what we have done. We have taken this electron to this side and we are getting this. We are getting a bond out here, positive charge is as it is, and now this oxygen is having these 2 electrons because these 2 electrons are moving out here, right? These 2 electrons are moving at this place. If the electrons will be moving to this side, I think it will not be having positive charge and this will be having positive charge out here. Positive charge. This will not be having positive. Electrons will be coming to this carbon also. So this carbon will be neutralized and the positive charge will be coming to oxygen because oxygen is coming to here. Here, look here. All the canonical forms should contain the same number of total sum of the shared electron pair and the unshared electron pair. Shared and unshared. Shared here is 2, unshared again is 2. 2 plus 2, 4. Shared here is 3, unshared is 1. This is 4. So they will make canonical. So this is very important. All the canonical forms should contain the same number of total sum of the shared electron pair and unshared electron pair. And the most important thing is their energy should be by and large be same. As we have seen in the case of another substance where we had 6 electron and their energy is become very high. That does not form. Okay. Let us try to understand one more thing. It is not acceptable to leave after breaking the bond in resonance. Suppose we are having this compound. This is a radical. This is the representation of a radical. Now this radical can be expressed in 2 different forms. These 2 are resonating structure of each other. These 2 are resonating structure of each other. Now if these 2 resonating structures are there, suppose we are doing like this. We are breaking this bond like this, making it a radical here and making it a radical and then leaving it there. So if we are doing it, whether this will be a resonating structure or not, obviously it will not be resonating structure because as I told you, it is not acceptable to leave after breaking the bond in resonance, right? First and second are canonical structure, but the third is not the canonical structure. Got the point? Okay. Coming to one more aspect of conjugations. What are the types of conjugation as we are talking? We have one type of conjugation called as pi sigma vacant orbital conjugation. Pi sigma vacant orbital. Look here. We have a pi here, we have a sigma here and we have a vacant orbital here. For vacant orbital, atom can have positive charge or can be neutral too. Both the things can happen. So we can draw various resonating structure and resonance hybrid for this particular compound. So this is what is called as pi sigma vacant orbital configuration. Like if we have CH2 double bond CH2 with a positive charge. Let us try to understand how can we make canonical structure with it. Electrons will be moving from this place to this place. So we will have CH2 with a positive charge here and this is CH double bond CH2. This is another canonical structure of it, right? And if we have to draw the resonance hybrid of this, we can draw the resonance hybrid like this, CH2 and we will show with a dotted line here, delta positive here, delta positive here. This will be the resonance hybrid of this particular compound. right? Okay. We can draw the canonical structure of benzyl carbocation also. Look here, this is what is called as benzyl carbocation. How are we drawing the resonating structure of various compounds? Let us try to have. In benzene, we have considered there is a double bond here, double bond here, double bond here. We are talking about the static electron theory. The electron will be moving from this place to this place. There will be a double bond and it will be neutralizing the positive charge. The positive charge will be coming to this place. Another way, this electron will be going to this side, the double bond will be going, and this is how we are showing the resonating structure of benzyl carbocation. And benzyl carbocation resonating structures will be drawn like this, right? We can also try for cyclopropyl carbocation. Cyclopropyl carbocation. We have cyclopropyl carbocation like this here. You can move electron from this place to this place. So electron, if it has gone from this place, this will be forming, coming to this place, and double bond will be coming to this place, right? Now this electron will be coming to this place. No, I'm sorry, make this electron go to this place. So again, we can form like this. Positive charge will be coming to this place and double bond will be coming to this place. These are the resonating structures of cyclopropyl carbocation. Due to resonance, the charge gets distributed and volume charge density decreases and stability increases. Let us try one again very important question. We have drawn these two structures, RCOCH2 plus and RCOCH2 with a double bond. Are they make canonical structure? Are they make canonical structure? Again, as I would like to remind you, the second structure is highly unstable. What has happened, you can clearly understand. What has happened, you can clearly understand. The electron has gone from this place to this place, making carbon negatively charged, and CH2 plus, this will be forming a double bond. An electron is going from this place, it is having a positive charge here. And this is forming. This particular oxygen is now having 6 electrons, 2 from this place, 2 from this place, 2 from this place. It has 6 electrons only. And the potential energy of this is very high. So it is not an acceptable canonical structure. So no resonance in the molecule, despite having sigma, pi and vacant orbital. Right? So these are some conditions which you need to understand. When you are forming the canonical structure of different species, then you should bear in mind that their energies should be comparable. It's not like one should be having a very high energy, another will be having low energy, and it will be forming like this. Okay. Another point which is worth noting. Atom having positive charge should have a vacant orbital. Look at these two examples. It has pi sigma positive charge, pi sigma positive charge. But here it is important to have vacant orbital. It's not always necessary that pi sigma positive charge will always be having resonating structure or resonance. There should be vacant orbital. Look here with NH3 and with OH2, despite they are having positive charge, they can have positive charge and their octet is completed, they do not have any vacant orbital. Here N and O, despite having a positive charge, have 8 electrons and there is no vacant orbital. So they will not show resonance. These two compounds will not show resonance. Right? Coming to the last aspect of it. Okay, I think we have done with it, and hope you have enjoyed the session of resonance, and I hope in the coming second part of the resonance we will be elaborating more on resonance, and you will be enjoying it much more there. Thank you very much.